So good morning. Today I'm delighted to introduce Professor Satya from Carnegie Mellon University. He has a long history of exciting and impactful projects in mobile computing, mobile systems areas, including OpenAFS, CODA, ISR, Diamond, and was also pioneered the concept of Cloudlets with a number of projects. And today he's going to talk about the Wearable Cognitive Assistant, which is an FRA-funded project and combines cloudlet concepts with Google Glass. Please welcome Satya.
Thank you very much, Roy. Thank you very much for the introduction, Roy, and thank you all for coming. What I want to tell you about is work that we're doing on an idea that is very cool, and I'm very excited about it. I'd like to share it with you. It's work that's partly funded by Google, both in terms of a research award and also Google Glass devices, which you guys gave me. So, like so much else, this is collaborative work with a long list of collaborators, two of whom are in the room, both Roy and Nigel. Certainly the concept of cloudlets is something that I developed in there in collaboration with them, and it's part of the foundation for this work. So we live at a very, very unique moment in time when three completely independent innovations are coming together. And so let me just take a moment to explain what these three independent innovations are. On the one hand is wearable hardware, stuff like Google Glass, Microsoft has HoloLens, there are other wearable devices on the market. There's going to be a big fight in the marketplace over the correct form factor, the correct devices, et cetera, et cetera, et cetera. But there is no question that the time has come for wearable devices. So that's one force. The second force is the convergence of mobile computing and cloud computing. So as we speak, there's a commercial product from Nokia called RACS, Radio Access Control System, a cloud system, and it's a commercial product that they sell, where there's a Xeon computer right at the transmitter. In September, in London, there is a conference, the Mobile Edge Computing Conference, which is by cell tower operators, specifically for computing at the edge of the internet. So this whole concept of cloudlets that I mentioned, which are small clouds close to the edge, close to mobile devices, is another force that has happened. The third force, which is not hardware, but really software, deals with tremendous advances in what I broadly characterize as cognitive algorithms. These are things like computer vision, face recognition, object recognition, language translation, and so on. All of these. Google certainly has many, many innovations in this space. Last year's publication at CVPR, the Computer Vision Conference, by Facebook researchers, showed a face recognition algorithm that was as accurate as human beings. And last week, I believe, Google researchers showed one that was even better. So this is happening. So the research that I'm about to describe to you asks the question, what can you do at the intersection of all of these? This tiny little red spot with the intersection of wearable devices such as Google Glass, leveraging cloud resources to extend the computation, to do big data computations if needed, combined with the progress in cognitive algorithms. What could you do? So what you can do is something that is really quite science fiction-ish. Let's take Google Glass, since all of you are familiar with it. When you wear it, all of its sensors see what you see, it hears what you hear, it senses what you sense in terms of accelerometer, gyroscope, etc. Imagine processing that sensor input in real time on a cloud and getting the result back faster than the person can think. Within the inner loop of human cognition, and if I can constructively give advice to the user, saying, here's something you could do, or here's an action you could take. That would be something that has no equivalent today. So I think of it as really a new modality of computing. And the emphasis, as the slide mentions at the bottom, is seamless integration into the inner loop of human cognition. Now, what's hard about this? What's hard about this is you have to be very, very, very fast. You have to be able to process the sensor inputs, produce the output, and then have time left over to do something constructive on behalf of the user within the time that the user has to process the same data. And if you look at the psychology literature and the cognitive psych literature, the typical speeds are in the hundreds of milliseconds range down to tens of milliseconds. So some things are pretty amazing. Humans, for example, can tell the difference between a human sound and a non-human sound in 4 milliseconds. You can see how evolution might have equipped us with this. If your child is lost in the woods and you're in the old, ice age or something, that might mean the difference between being able to rescue the child and not. So there's debate over exactly how fast is fast enough, and I honestly don't think we will know the answers until we build these things, experiment with them, etc. As a working guideline for our research, we've used the number few tens of milliseconds. So few is obviously soft. 10 milliseconds, I'm certain, is very good. 20 might be okay. Once you start getting much further than that, we start getting into periods where at least some of the cognitive measurements that people have reported start to be larger, start to be comparable to these numbers. So people have used the term tactile internet to suggest a cloud-based system that is so reactive that it responds in the way that I just described. So think of the tactile internet as a platform or a medium for wearable cognitive assistance. So how do we do anything with this kind of time scale? 10 milliseconds is very little time, right? Really very little time. The best way to do it, by far, would be to do it all on the mobile device. No question, okay? Unfortunately, it doesn't work. Here is optical character recognition using Tesseract, which is a Google open source OCR, on Google Glass. That's the standalone measurements. 10 seconds to do the image recognition and roughly 12 joules to recognize it of energy. If you are able to ship the image from the camera to a nearby cloud processing entity, even after you pay for the cost of transmission and reception, it is 10 times faster, 1.3 seconds roughly, and about an order of magnitude less energy. So in general, wearable devices especially, it's true of all mobile devices, but especially true of wearable devices. Weight, form factor, heat dissipation, comfort, these dominate over processing capability. And so if you asked a user, would you like a Google Glass that weighs half as much or can process twice as fast? It's very clear what the answer will be. They will want one that's half as heavy and perhaps cooler and the battery life is longer. Okay, nobody will say, give me a more powerful Google Glass. So standalone applications don't work. And in fact, just waiting longer, maybe next year's next year's hardware from Qualcomm or whoever might be faster. This graph from Jason Flynn's synthesis lecture on cyber foraging says that waiting is not going to help. If you look at the columns, they show you the improvements in compute power over roughly a 13-year period in server hardware and in mobile hardware. In each column, the improvements are dramatic. But if you look horizontally, At every level of technology, there's a substantial gap. And I refer to this as the mobility premium. This is what you pay to make something mobile. You have to give up something at any given level of technology to meet the human considerations that I just mentioned earlier. Heat, dissipation, battery life, weight, size, etc. Okay, then if you can't do it all standalone, then the right thing to do is to offload it to the cloud. There's Google Cloud, there's Amazon, lots of cloud services. The problem is you aren't going to get an answer back fast enough. The measurements reported in the literature on the average latency between a random mobile device and the optimal Amazon cloud is of the order of 75 to 80 milliseconds. That's just getting the packet there and back, zero processing. So if you add to this any processing, and then you need time left over to do some constructive guidance for the user, you're dead. So offloading to the cloud doesn't work. And so the answer here is the concept of cloudlets, which are data centers, data center caliber compute, but located close by, located one wireless hop away. Where they are located is somewhat independent of the rest of this talk. They could be in a base station, they could be in a cell tower, they could be in a machine room in this building, LAN connected. All of those would be perfectly acceptable. Okay? But the important point is that the round trip time is significantly less than 10 milliseconds, which means that you have many milliseconds of budget for processing the sensor data and then composing some constructive feedback to help the user. Yes? Yep. I have numbers. I don't have it right here. I have many numbers, many measurements. Maybe at the end of the talk I can dig them out for you. So the question was, what is the average time for example, shipping image data to the cloudlet and back? To a first approximation, it's the last hop wireless bandwidth, which, if it's Wi-Fi, today it can be as good as 400 megabits per second, right? And then you have to add to it some latency that is true even for a zero-length packet. But it's typically in the single-digit milliseconds, okay? For even a 1080p video frame from a mobile device, it's of the order of single-digit milliseconds, okay? So this picture shows you our vision of cloudlets. The talk is not about cloudlets. It's merely, cloudlets merely happen to be an enabler of the class of applications that I'm describing to you. So our vision of cloudlets is that someday soon, maybe within the next decade, you're going to see these things not just in buildings, but in automobiles, next to your battery and your spare tire. It's a cloudlet. Remember, for the foreseeable future, the best connectivity between an automobile and the cloud is going to be 4G. Your connectivity to the cloudlet is going to be a lot better inside the automobile. In an aircraft, same story. I had Wi-Fi on my flight, but it's the worst Wi-Fi internet connection I've ever experienced. Okay, latencies were horrible when it worked. So we see a world in which cloudlets are widely dispersed and everywhere, and that's the underlying assumption for the rest of the talk. So what can cloudlets do for you? They can do many things. This talk is about taking advantage of latency. Things I'm not going to talk about are how running analytics, for example, computer vision analytics or video analytics at the edge on a cloudlet can actually save you tremendous ingress bandwidth into the cloud. Privacy, one of the biggest barriers inhibiting the Internet of Things, is people's concern about their private data, sensor data, leaking out into the web. If users had confidence that a trusted piece of software that they trusted, it's not somebody else's software, that they trusted, ran on hardware that they controlled and did initial analytics on the sensor data. And only the redacted data was exposed to the rest of the world. That confidence is likely to be a big enabler in terms of acceptance of IoT. So I see Cloudlets playing an important role that is a privacy. You can think of it as a privacy firewall. We think of firewalls as preventing bad stuff from coming in. This is about preventing, well, depending on your viewpoint, good stuff or bad stuff from leaking out, okay, in the other direction. A last point is Cloudlets can also be useful if you can't get to the cloud. If I'm in Nepal and an earthquake hits, or here and an earthquake hits, or a flood happens, Hurricane Sandy hits, or something like that. There's so many natural disasters that happen. And in those scenarios, as well as military scenarios, getting to the cloud is not always possible. So these are all the unique values of Cloudlets. In this talk, we're only going to focus on the first of these, which is it provides you low latency. And to complete the thought about Cloudlets, this is not hype. Shown in this slide are pictures of pieces of hardware you can buy today. They're real commercial products. They're called micro data centers. They're actually used for a variety of purposes, but they're not being used in the way that I'm describing them in this talk. They're being used primarily as private clouds rather than second-level cloud entities. So the vision that I have for Cloudlets is that you have today's cloud unmodified. All of the major vendors are up there. But you have at the edge what I consider to be second-level cloud representatives. These are caching sites which cache virtual machine state from the cloud, which may have data cached from the cloud. You can blow one up, roll in a new one. It reprovisions from the cloud and provides you the services you need. So that's the vision. And notice how it's vendor agnostic. So you don't think of a Wi-Fi access point as being an Android one or an iOS one. The same way, I think of Cloudlets as being vendor neutral, that they are completely agnostic regarding the specifics of the vendor. So think of this like a CDN, except it's for computation. What Akamai did for data, we need to do for computation. So on top of Cloudlets, to build the kind of applications that I introduced at the beginning of the talk, wearable cognitive assistance, we have built an architecture called Gabriel. Gabriel is an angel, so it's like a little angel that sits on your shoulder and offers you helpful hints as you go about your business. So let me walk you through. I'm going to point at the picture. Unfortunately, I don't think there's any way. Well, maybe there is. Maybe I can use my mouse. Candice, can you see my mouse moving? No, on screen. No? All right. This is one case where the people in the room will benefit. We have here the sensor data being streamed from the video device, from the Google Glass. It goes to a collection of virtual machines that all together constitute an ensemble that's working on behalf of this user. This is pretty heavyweight stuff running on a data center, a small data center close by. Each of these thick black boxes is a virtual machine. And each one encapsulates some piece of very complicated software, such as object recognition or speech recognition, that may have been written for diverse environments. Some may be written for Microsoft Windows, others for Linux. Some may have been written in C#, others in Java. The reason that we use virtual machines is to allow us the greatest flexibility in mixing and matching these, almost in a slide-in way, plug-in way. The decoding of the sensor data is done by one entity, and then there's a publish-subscribe interface. Think of it like a bus that disseminates the sensor data to these cognitive engines, as we call them. the outputs of the cognitive engines go to an entity, which is the entity that understands what the user is trying to do and to help him or her. We call this the user guidance VM. So the thickness of the line is roughly the amount of bytes that are transmitted. So you can think of the raw video data coming in and being disseminated as a lot of bandwidth. But after your object recognizer says there's a person there, or there's a rock there, or there's a dog there, that's very few bytes. Okay? And the synthesis of this and the giving of advice to the user is the essence of what wearable cognitive assistance is all about. Then you need to do this whole loop from the frames, the decoding, the recognition, the interpretation in the context of whatever the user is doing, and then any helpful advice. This whole loop has to be of the order of a few tens of milliseconds. And the reason you need all this to run in the cloudlet is you're destroyed if you take 70 milliseconds to even get your packets there. Okay, so this all sounds great. What's the killer application? What is it people will really spend money for, will actually want to do? You know, if Google Glass survives and Microsoft HoloLens survives for a long time, what are the kinds of applications in which it will really, really make a difference? Let me walk you through an example. So cooking, all right? Here's a guy wearing Google Glass doing cooking. One of the earliest apps that came out for Google Glass was the recipe app. So if both your hands, you're kneading dough, or both your hands are dirty, you know, you can still see what to do just looking up at your display. Really helpful. But let me tell you what this recipe app does not do. Here's what it doesn't do. A good friend standing next to you would say, no, don't put it in yet. The oil is not sizzling enough. That's something. That's because the recipe app is not leveraging the sensor inputs from the wearable device. Now, all of you in this room, without exception, have used a system which works like what I just described. Okay? Except you don't think about it in these terms at all. Think of GPS navigation. It knows what you're trying to do. You told it where you wanted to go. It has exquisite, detailed knowledge about the task. It's got all the maps already worked out. It uses sensor input, only one, GPS. It doesn't use video, it doesn't use accelerometer, gyroscope, audio, no, just GPS. Pretty crude. But just that combination is already useful to you. It tells you step by step what to do. And if you mess up, like you didn't take the exit, the voice may get a little panicky, but it recovers and says take a legal U-turn at the earliest opportunity, or whatever the fix is. So there is an example of exactly the kind of system I'm talking about, except of course it's not wearable, it doesn't need to leverage cloudlets. It's a highly optimized, one-of-a-kind system, but the metaphor is the right metaphor. So could we generalize this metaphor? What are the kinds of use cases one can think of? Let me just share some hypothetical ones, and then I'm going to show you some real ones that we have built. Okay? These hypothetical ones are for the future. Think of assembling a consumer product. You go to Home Depot or Lowe's or whatever the local big box store is here. You buy a grill, and it comes in a big kit with instructions. And God help you that weekend. Okay? If you're like me, I have put 2 grills together in my life, and I made a mess of both. Or IKEA, you go to buy furniture there, and you get this thin printed sheet with no words, just pictures. And of course, after you put piece A and piece B together, 3 steps later, you discover you used the wrong piece B. You actually should have used the short one, not the long one. And of course, once they're put together, you can't separate them. So now you have to call IKS 1-800 number, somebody has to field your call, they have to mail you a replacement, etc., etc., etc. Think of how much easier it would be if I could put on my wearable glass and IKEA gave me an app for that specific gadget, and just as I'm about to insert the wrong part, it says, no, not that one, right? A specific closely related situation to this is in industrial troubleshooting. If you look at companies like Siemens, ABB, any of these large industrial companies, a huge amount of effort goes into industrial troubleshooting. The amount of expertise needed is a lot, and there are very few people who possess it. And the ability to share this through an app kind of mechanism that I just mentioned would be very powerful. Closely related, training of doctors. So in this picture, the person lying down, the patient, is actually a mannequin. It's not even a real person. So this is how the earliest part of a doctor's training typically happens. Yet you need the expert who's standing next to him, because there's no other way to explain to the doctor exactly how to do whatever he needs to learn how to do. The scarce resource here is the experienced doctor. To the extent that I could replace him by an app of the kind I just described. Maybe you can't do it for real patients, but certainly during the training phase with a mannequin, right? You don't have to worry about malpractice lawsuits. Very closely related is instruments, especially for elders, where they have to take either blood pressure, glucose, all kinds of health care. The instruments have to be put on correctly, otherwise the data is invalid. For a senior person who's living alone, unless you have somebody checking on them to see whether they're doing it right, this kind of self instrumentation doesn't work very well. And the guidance on these devices is very poor. There's very little incentive for the manufacturers to give you clear, good instructions or to have a good user interface. Once it gets FDA approved, you're done. So this is another case where step-by-step guidance, correction from error, etc., would be helpful. And then my favorite is, of course, just as you're about to do that evil act of putting a calorie-rich donut in your mouth, it stops you and says, stop, don't do that. Okay, so this all sounds great, but we're a long way from that. The amount of work still needed ahead to get to do any of these seriously challenging but also valuable tasks is some distance ahead. But we have some initial evidence. I would call these proofs of concept, and that's what the rest of the talk will be. How many minutes do I have, Roy?
15.
15, perfect. Okay, so we just reported a workshop paper at the most recent Mobicis conference in Florence. So if any of you are interested in many details I'm going to gloss over in the 15 minutes, just go take a look at this. So about 9 months ago, about September or so, 2014, we put together what, to the best of my knowledge, is a very first example of such a cognitive assistance application. So let me show it to you.
Once the task is loaded, our system will provide both visual and verbal guidance to the next step.
This is the video camera output of the Google Glass, and up there is what you see on the display.
Welcome to the Lego task. As a first step, please find a piece of 1x4 green brick and put it on the board. Excellent. Now find a 1x1 white piece and add it to the top of the current model. Good job. Now find a 1x1 black piece and add it to the top right of the current model. Great. Now find a 1x2 white piece and add it to the top of the current model. Now find a 1 by 1 green piece and add it to the top left of the current model.
Once you did something wrong, our system will tell you how to fix it.
You are quite close. Now slightly move the 1 by 1 green piece to the right by 1 brick size. Great. Now find a 1 by 1 green piece and add it to the top left of the current model.
Okay, and it goes on. So you get the basic idea that, this is what goes on. How does it work? Here's what happens. And since it's the first one we built, we looked at what we built, and then we built a couple more, and the pattern that's emerging seems to be quite similar. There seem to be two phases to the whole processing. The first phase is taking the raw sensor input, in this case the video frame. It only uses video. We didn't use the audio or any of the others. But future applications would obviously use all of them. Now, this input is completely unstructured. It's the student's office, it's some lighting, like this kind of fluorescent lighting. It works equally well if I do it in a conference room with a big window and sunlight. So the lighting levels, lighting colors, there's no careful control of this. So somehow, regardless of what clutter there is and what kind of variability there is in the input, you need to extract this piece. That's all that is relevant to the task. And in fact, the way we represent it internally is as a simple matrix there, where the number tells you what color. Like 0 might be no block, 1 might be white block, 2 might be red, and so on. So that small matrix contains all of the useful information relevant to the task from this many, many pixel video frame. So we think of this almost like analog to digital conversion. You have a huge state space up here. You have a much, much more constrained state space relevant to the task, and the extraction of that, in some sense, an A to D conversion is the hard part. And then there's a separate step where you compare the extracted state to the expected state. And the difference between the two guides you, offers you guidance. Now, how exactly do you process that frame? That turns out to be tricky. So just, this is not a talk on computer vision, but just to give you an idea of the processing that has to happen per frame, here's what happens. You take the input image, you basically do a black and white transformation, you find out where the board is, then you know that the board is rectangular, so you find a quadrilateral, and from the quadrilateral you can estimate what perspective correction you have to place on the board to make it look normal. Now you have to find on the board the little part. You typically do that by edge detection, finding out the connected component that has few edges, and then it turns out now that if you aren't careful, the fact that this isn't really two-dimensional, these blocks have some slight thickness, it turns out to mess up the color detection later. So we actually had to add the detection of the sides and then make it upright, and as close to final step, you have to determine the colors of the pieces. And the magenta areas indicate uncertainty. And what you do in the final step is then use a weighted averaging technique to then convert it into the matrix. And once you have that matrix, generating the synthesized image is trivial. So it's very much like from here to here is analog to digital conversion, and from here to there is digital to analog. And as you all know, the latter is usually trivial. It's the first one that's the really hard part. So it took us, none of us was computer vision experts, so Rahul Suktankar, who's a Google employee, worked with us remotely. He helped us and guided us. It took about 4 months of our time to write just this part, not the rest of the application. So let me show you 2 other applications, and then I'll wrap up. So we built this application from scratch. So we asked, is there some off-the-shelf application that we could take that's already there? We didn't write it, somebody else wrote it, they found it useful. Could we extend it with Google Glass in the approach that I just described and create a cognitive assistant out of it? So it turns out that we found this program called the Drawing Assistant. It was written by folks at INRIA in France. It's published at WIST in 2013, so it's about 3 years, 4 years old, not ancient, it's pretty recent. And here's what it does. In figure A, you can see that the user is drawing on a tablet. This is a mouse-like thing connected to the computer. And he is shown a drawing on the screen, and his goal is to try and mimic it. And there are many ways in which the system can help the user sketch. So for example, the blue lines are one kind of technique. There's a skeleton kind of technique, just as if you were using Kinect. Then there's another approach using grid, and this application offers you the choice of whichever one you want. The interesting part is when you draw on the tablet, if you don't do it right, you'll get lines like the red line there, which guide you and say something is not at the right angle or something is off, and you can, if you understand the feedback, then you can correct it. So our question was, to use this today, you have to be tethered. You have to be connected to a desktop, you have to have a tablet, etc., etc. Could we make this hands-free? In fact, if I had a surface like that wall on which presumably I can draw, could I just use that? Could I use canvas and oil paint, crayons, right? Completely untethering an existing application. And so, in fact, that's what we've been able to do. So this is an example of the back end of the application is unchanged. What we do is we change the front end. This is the camera image from Google Glass. The symbolic representation, this is the A to D conversion, is extracting that piece. And if that piece, that digital representation, is exactly what the application already expected, then all of its complicated logic works just as before. So let me just show you this.
In this application, we have built a drawing assistant to help you practice drawing by observation techniques. For any target object, it offers blue construction lines for a user to follow and provide corrective feedback.
We just sped up the video because it's too slow otherwise.
Once a user's sketches are detected, our system compares it with the target outline in our database and shows on glass how a user can improve the drawing. The red parts of the feedback outline indicates erroneous drawings. The red dashed line illustrates incorrect alignment between corners of the outline polygon. Now the user has followed the guidance to fix the right part. As you can see, the resulting outline is much more accurate. Our drawing assistant is also able to provide guidance when a user is drawing with other media. For example, the user now is drawing with a marker on the whiteboard. The application again recognizes the user's sketches and shows feedback on the glass.
Okay, so this is interesting. It's an interesting approach. How many complex logic interactive systems are there where you could replace the front end with a system like the one I've been describing and completely untether the user, not just in terms of away from the computer, but even in terms of the medium that the person uses to interact with. So both these examples, you know, the latency argument is there, but what happens if it was really slow? You know, the user might get bored, the user might get a little irritated, but it's not going to be devastating. So we try to come up with a use case where latency was absolutely essential. And so what we came up with was a ping pong ball guide to help you play better ping pong. The assumption is you already have decent hand-eye coordination, but maybe you aren't good at strategy, about where to hit to the left or to the right. You know, we're not trying to help a blind person play or any such fancy stuff. This is assuming you're a normal person. And so what we have to do is detect the ball, detect the opponent in 2 successive frames, and detect what is happening. Which way is the ball headed, which way is the opponent headed, and then whisper guidance before you hit the next ball. So there's very clearly latency considerations. Okay? And the ping pong ball detector, in the interest of time I'm going to skip, is non-trivial. But here's a few seconds of this.
Our Google Glass-based ping-pong assistant helps the user to play better ping-pong by whispering whether the user should hit to the left or to the right. The hint is based on the observed ball position and opponent position.
So what you're seeing, this camera is a video from the Google Glass. The guy is playing it very
Left. Left. Right.
As you can see, we always guide the user to hit the ball to the direction that is harder to defend.
Obviously, these are baby steps. There's tons of refinements, improvements, making the whole thing real. But just think about that ping pong example. There's a case where latency really matters. Telling you the perfect tactic after the ball has passed you by is not very useful. Okay? One last point. I don't have a video to do this, but we knew that there was a ton of YouTube videos on how to do useful things, how to make the perfect souffle, how to make the perfect omelet, how to fix your carburetor, how to fix a broken washer. And today, to use one of these things, you Google for it, find the right video, and then search for it. And one of the interesting questions was, could a system like this, just by looking at what you're doing, suggest the right video? It wouldn't be closed loop. It wouldn't be like these 3 examples in that we're not sensing the environment after you start viewing the video. So it wouldn't correct you. But it's partway there. It's not closed loop. So the way it works is use a live video stream, and then you use feature extraction and extract keywords to describe what you might be doing. Okay? And then you use that to an index database of YouTube videos to suggest ones that might be useful. Okay, so I don't have a live video of this. It actually is a bit too slow at the moment because this step, the feature extraction step, is actually definitely not real time. If you're looking for a performance problem to attack, there is one that could make a huge, huge difference. All right, I will close now with just 2 thoughts. I started out by explaining many real-world use cases which I think await us. I'm very excited about this work. I think it's opening the door to a very new use of wearable devices and cloud processing in a way that we've not seen before. So my prediction, you heard it here, is that in the next decade, the killer app of mobile computing will be this class of applications. And the kind of low latency, high computational demand processing that you need to make this possible will not happen unless you have pretty capable small data centers close to the mobile devices. Thank you.
Okay, so let's take some questions. I forgot to mention earlier that there is a dory associated with the calendar item, so if you don't want to speak up and just want to type in your question, then please add it to the dory. But if not, we can take it over the the VC link and in the room. Do we have a question? There's a question there. Nigel?
Yeah, I was really interested in the example that you gave of the sat nav. And when I think back to the really early tour guide stuff that we did, that felt like a cognitive assistant, and we tried very hard to make people believe that it was a cognitive assistant. And we said, imagine it's like your friend. You don't need a map. This thing will tell you where to walk around. People stressed immensely about this, and in the end, we gave in and gave them a map. And with a sat nav, you get a map as well. I was kind of curious with this cognitive assistance, how much of it you think it's going to be doing active, just telling you what to do, following your steps, and how much you think it's going to have this, how much of it does it need to lay out from a map in front of you to follow the instructions?
So I don't know if everyone heard that. Should I repeat the question condensed? Okay. The condensed form of the question is, so the person who asked the question was Nigel Davis, who built a system called the tour guide system. This was in the mid-90s. If I remember correctly, it was before GPS systems became popular.
Yeah, before GPS.
So so the question that Nigel had was, in his experience, people were reluctant to trust the guidance from the tour guide, that they felt the need for independent validation. I submit to you that part of the reason is because they hadn't used GPS systems before. As you get more comfortable, you stop carrying the map. Okay? So it is possible that during a transitional period when applications like this are still buggy, people may still want the printed instructions from IKEA. But if we make these reliable and good, they're so much better that I don't carry maps today. In GPS, I trust. Okay? And it has led me astray on occasion, but the occasions are rare enough that I'm willing to overlook them. So I suspect that's part of what it is. But the bigger point is how much reassuring guidance should be displayed, for example, in the Google Glass display, to confirm to the user that the system does indeed understand what the heck is going on, and that its guidance to pick the object X up is based on credible logic, and it's not totally lost. I don't know the answer to that. I think we'll have to build more of these, gain more experience. We haven't done any user studies. It's a small group, my group, that is doing this, so I would love if people at Google were interested in working with me on this. After all, it's using Google Glass.
Other questions? Another in the room?
Hi. So you spoke about a specific type of variable, which is like heads-on on your. Another thing that you can add. Have you thought about the
So let me repeat the question. The person at the back who asked the question said that so far our guidance was predominantly audio, and one could imagine much richer feedback, for example, augmented reality feedback, where the image is overlain. You're absolutely correct. We have thought about it. We haven't built any simply because it's taken all the cycles we have just to build these. Understand that building these has not been easy.
I asked because I'm working on AR for that.
Oh, we would love to collaborate with you.
Yeah, so I was just wondering if you had any insights. We can talk about it.
We can discover the insights together.
Other questions? Another in the room?
Actually, two. One's on the box. What about entities where it's benefit to the so, for example, like what does
This is another excellent question. So let me repeat for the benefit of the people who are remote. The question is, the examples I gave had very tightly focused, narrowly scripted tasks. One can imagine much richer experiences, such as instead of teaching somebody how to draw that precise dog that's on the screen, you want to give them some artistic freedom and give them some latitude and give them some long rope and only rein them in when they seem to be getting lost. These are all excellent points. And the short answer is, I believe you are correct. I think those are legitimate. People will want them. We just haven't gotten there. It's down right. In fact, let me build on that question, because maybe this is the other question you had in mind. Our assumption in these initial examples that we're working on is you actually want perfect guidance. It's like GPS gives you detailed instructions. Even if you've been on this route before, it doesn't learn that you already know much of it. It doesn't cut back on the guidance. You can imagine a tutor whose job is to teach you to autonomously do this task without help. You would then need guidance. The analog to digital part would remain the same, but it's the task guidance part which would have to be much cleverer. It would have to build a mental model, internal model, of your cognitive state, and then decide, he's going down the wrong path. Should I tell him now, or should I let him cook for a while? Okay? And the first time around, maybe it tells you right away. But the second time around, maybe it lets you go for a while. Modeling the state of frustration of the user, etc. This is a huge area of learning technology. And I have colleagues at Carnegie Mellon. This whole area is called learning sciences, and they're learning tutors. But what is very interesting is, for example, that there's a commercial product called the Algebra Tutor, which has been used in elementary schools in the United States, in LA, I think in the Bay Area, etc. And it has been shown to improve the grade, the caliber of the math done by the students. But all of it has to be done online, like that drawing program. Imagine we could take the back end of it, use Google Glass, and now on a whiteboard or a blackboard or on a piece of paper, the student does the math and he's helped. Now, you could argue, is that good or bad? Is this a skill people should need or not? We could debate that. But I think from a technical point of view, it would be very cool.
Can I ask? Sure. So the follow-up question was, it seems like
Thank you.
works so far, but what I'm wondering is there a way to kind of speed up greater progress?
A lot of what? That's another excellent question. Beautiful question, and it's a question that has occurred to us. Like so many other great ideas, and all those questions that were asked, we are limited in the resources in terms of people and time. And so, frankly, my personal belief is this is a huge area. There's far more than one research group can do. I would love to have many other groups work on this in parallel. We can carve up the problem space in different ways. The question you asked is right on target. All computer vision typically involves ambiguity. And resolving that ambiguity is not easy. If I had embedded sensors in a room like this, and I could supplement the first-person viewpoint, which is a camera on Google Glass, simultaneously with additional viewpoints, a lot of that ambiguity could be immediately resolved. Same kind of observation is true when you do sensor fusion. If I have, say, an accelerometer reading, I have a gyroscope reading, I've audio, and I have the video. And at the intersection of those, you can eliminate a lot of ambiguity And those are things we would love to do, but it's more than a small research group in a university can do. So I would love for you guys to work with me on this.
We should just check, see, are there any questions in any of the remote rooms? You may need to unmute if you have some. Doesn't sound like it. I'll just add one final question then from the room here. So one of the things you talked briefly about was sort of the resources needed for this kind of system. And the one that goes to me straight away is the issue of power. And you're having to stream all this this video, and there's some redundancy probably in what has to be sent where you can actually do the image recognition, but the benefit of not streaming so much is that the glass will last longer. What are your feelings about how to approach this problem?
An excellent question from Roy. You're right on target there. The best processing you can do with an image is to discard it, because you have discovered very early on that there's not enough interesting in it to even ship it to the Cloudlet. And so one of the interesting insights we got from doing exactly what you said, which is trying to both speed up and lower the energy consumption, was this discovery that in many, many cases, you can tell quite easily in a task-specific way. It's not, in an arbitrary way, but in a very task-specific way, whether you really need to ship the next frame. So for example, let me give you a simple idea. Think of object recognition. It turns out that if you aren't careful, when a person turns their head, the frames that are captured by Google Glass are blurred. That's just the way it is. Once you have a blurred frame, shipping it to the Cloudlet, doing object recognition on it, is all worthless, because it is going to give you pretty bad results. So if I could use my accelerometer or gyroscope or other image-centric approach to know pretty early, look, this is likely to be a blurry image. Let me not even bother shipping it. It turns out to be a net win. Even better, so we published a paper on this at Hot Mobile this year, and we call this concept offload shaping. That is, you're basically using a small amount of additional computation on the mobile device, like Google Glass, to decide whether it is in fact worth processing further. There's an idea called perceptual hash, which is you take 2 frames of a video and you generate the perceptual hash. And if the perceptual hash is close by, then the chances are very good that a human looking at it would say that they're quite simple. And so the key insight is computing the perceptual hash is actually quite energy efficient. Okay, so it's worth doing that on Google Glass, because then I can skip out of 30 frames per second. If I can ship very few because not much interesting is going on, you win huge. So those kinds of techniques are going to become very, very important. But what is important is also to recognize that what is important and what is not important can change abruptly, because the task state could change. It could be that up to now, the only thing that mattered was a certain kind of object. But once you reach a certain task state, it could be now that there are many other things that become important. And so there needs to be control of the early discard on the mobile device that has to be controlled by the higher level processing on the Cloudlet. So again, another deep area worth investigating very deeply.
Okay, thank you very much, Satya. Please, let's all welcome. Thank you. Thanks, Satya, for a wonderful talk.
Thank you very much.